4 here, so I can have a 4 here. This 4 times of this is equal to this difference. So I can apply what do you call triangle inequality, and I can get something like this. Okay? So I can get something like absolute of u plus v and u plus v. So I'm doing this proof. I mean, you can read it for yourself. It isn't anything too much complicated. Plus a u minus v and u minus v. Agree? Alright? So I just took absolute and just applied what they call triangle inequality. But usually, I haven't written one thing, but he's giving this guy a name, like an explicit name, and that explicit name is that this name actually, so numerical radius. That's what this guy is giving this name. Now the question is, and the next thing that we are having is this. The numerical radius of this is less than or equal to norm of u plus v square, okay, plus norm of u minus v square. The question is how?
Simple calculation.
A
u plus v को अलग कर दें, v को अलग कर दें, इस तरह से हो जाएगा.
Are you sure?
Yes, sir.
Do it for yourself. Okay. Don't put this one. Just do it in this way. Okay. But if this is the case, then this is same as numerical radius of A times, I can put a 2 here, 2 times of norm of u square plus norm of v square. Okay. Because I can rewrite this guy in this manner. So it's like if I write this in inner product and do simplifications, and I'm going to get this guy. And what I'm going to get in the end? I'm going to get this in the end actually. Get this in the end. That is that if we replace in this inequality, the last inequality that we have got, like this one times like less than or equal to the last inequality. This one. So if we replace V by CV, okay, but C is some constant, it's like a complex number, but its absolute is 1 actually, its magnitude is 1, okay. So we're going to get 4 times of real part of AU and C times of V. And this is less than or equal to numerical radius of A times norm of u square plus norm of C times what is called V square. Okay. We are going to reduce next if this guy, the 2 times of AU V, okay, we can get 2, just simply dividing both sides by 2, and this is less than or equal to numerical radius of A, okay, times norm of u square plus norm of v square. In other words, what essentially you want to do is that you want to get rid of this real part. Okay, so it's like you want to get rid of this real part. Okay, and now taking the supremum over all over f. So now I'm taking, okay, so what he is doing next is this. So taking
supremum.
So taking the supremum over, right, so should I take supremum here or here? Sorry. So I need to take the supremum here. Okay. So let's,
रियल पार्ट असल में ये यही रियल तो रियल पार्ट लिखने की जरूरत
what do you mean by that?
क्योंकि हमने प्रूव किया है
No, no, the real part is this actually. So you have to be careful.
F with F.
So F with F actually, not in general.
अच्छा
So the F with F is always there. Okay. Anyway, so let's take supremum. Okay. So let's take supremum. Okay. Overall, maybe on both sides. So take the supremum on both sides with the assumption that norm of u and the norm of v is 1. Okay. Or maybe less than or equal to. And do something similar here. So it's like take the soup, okay, with norm of u as 1. Take the soup with the norm of u equal to norm of v equal to 1. Okay, and what we have here is the numerical radius actually. Okay. If we have this, what are we going to get? So this side is going to become what? This side is going to become 2 times of norm of A, and this side is going to become, so it's like, okay, this is 1 and this is 1, so it's going to be 2 times of numerical radius of A. Okay? And what did you get? You get norm of A less than or equal to numerical radius of A. Now you can ask that why this guy is like, okay,
Why this is not?
why this is not? There is an exercise, okay, in Hilbert space, what do you call, chapter where the Hilbert space was introduced, the first chapter, which says that the norm of the vector can also be expressed in this manner. Okay, have a look on that. So the norm can be written in this manner, and hence you get what you want actually. Anyway, so bit of silly calculations, but you know, make careful calculations and then.
Include here, the second
Good one.
step. What time real interpedal?
Any absolute तो ऐसे है, I know that the real part of a complex number is always less than or equal to the magnitude of the complex number. So this is true in general.
वो सब पहले यूज करके आए शुरू में
हाँ?
वो स्टार्ट में यूज करके आए
नहीं, हमने start में नहीं.
ये सर फोर टाइम्स रियल ऑफ दैट वन इज
But
देयर
it's fine actually. So why can't I use it again? I can use it again.
मतलब भाई इक्वल नहीं हो जाएंगे इक्वल
नहीं, यहाँ जो इस्तेमाल किया है, okay. यहाँ जो so something that we have used here is this, that if I have a real number, so it's like I have a real number, the real number is less than or equal to the absolute, because this is real and this is real. So now I am saying that the real part of a complex number, okay, is what do you call it? Complex number. Okay.
So you cannot compare this way.
compare नहीं कर सकते.
इनको कोई फर्क
Are
पड़ेगा
we?
नहीं कोई
Okay,
फर्क
so
पड़ेगा नहीं कोई जाएगा
as we say that, like going from this part to this part is a mystery. So then we have to look to the appendix for the details of it. वो जो refer कर रहा है 8.1, I think he has made mistake. It's not 8.1, it's 8 point something else. So we need to get into the details. Okay. Anyway, it's a okay. It's not a very furnished proof, but it's something that gives you picture and bigger picture, and you can complete it for yourself. If you get trouble, maybe you can discuss it one more time. Which one? This one? No, it's because that this and this are one. These are one actually. So it takes the supremum with the norm of u and v as one, so we get both. So in other words, this part of calculation is bit here, so you have to be bit careful. So something that he is referring to appendix, you have to figure out that okay, what is in appendix this, which basically that's with it. Let's finish up this section. So I want 10 minutes more of yours because I came a bit late. So let's finish up this thing. So what does this result is telling us? This result is telling us that if you take AF and F, okay, then it's always real number, and you can compare the norm of an operator by taking the supremums of AF and F in the product of AF and F. So here are some of the pretty nice and simple basic properties. A set of lemmas and then just mention one or two result. So here's a lemma. Let's use these and read these results that we are doing in hand about self-adjoint operator, like very carefully, because this is one of an important topic, okay, from both point of views, mathematical point of view, maybe exam point of view. You can see the appendix and finish up and what you call polish this proof. So we have almost done this proof. Okay. And it's a small proof, it's not a big proof. It's a small proof. Okay, so here is the thing. Let A be self-adjoint operator. So it's like self-adjoint on H. Okay. Then following are true. And H is obviously Hilbert space. Okay. Then following are true. A. Every eigenvalue is real. Okay, so every eigenvalue is real. Self-adjoint operator never have complex or any other eigenvalue. Okay. The part is that eigenvectors are orthogonal. Eigenvectors orthogonal, orthonormal. Eigenvectors corresponding to different eigenvalues are orthogonal to each other. Okay? They are orthogonal to each other. Second part, and the third part is if F is A invariant, so it's like operator invariant, we mean by that, that is that if you apply A onto the, so it's like if F, which is a subspace of H, and it's A invariant, okay, then what I mean by A invariant, that if you compute the image set of F under H, it's contained in H actually. Contained in H? No, contained in F itself. Contained in F. So, A invariant means that take a subspace of H and operate A onto the whole subspace and you still fall into
The images are
the same subspace. If A is A invariant, then F perp is also A invariant. Haven't you seen this notion of invariance of subspaces in linear algebra? Pretty elementary notion. So it's like a subspace is called invariant, that if you operate a transformation on it, images fall on the same subspace. You haven't seen it? You see it now. And I'm adding another part into it, okay, which says that if A is compact additionally, okay, if A is compact additionally, then what? There exists an eigenvalue, there exists eigenvalue lambda such that what? Such that the magnitude of this eigenvalue is equal to the norm of the operator. Okay? In other words, so if A is compact along with being self-adjoint, then you can always find an eigenvalue which can achieve the norm of the operator. Okay? So what are the key properties of it? Self-adjoint operators. So like we saw AFF is real, okay, and we saw one property about its norm, and the second and important property is that every eigenvalue is real, okay. In other words, which is also sometimes called that its resolvent set is real, okay. Eigenvectors are orthogonal to each other. I mean, if you have multiple eigenvalues for an operator, self-adjoint operator, obviously you're going to have multiple eigenvectors, so they are orthogonal to each other. And the third thing is that if you have a subspace of F, H, okay, and that is invariant under A, in other words, that A of F is contained in F, then its perp is also A invariant actually, okay. In other words, A of the perp is also going to contain in F perp. And the third thing is that if A is compact in addition, then there must be an eigenvalue such that whose magnitude can achieve the norm of the A. It's a pretty nice simple proof. Okay. So everything. So let's begin with the first part actually. Okay. And I would like to show that every eigenvalue is real. So let lambda be an eigenvalue such that AF is equal to lambda F. And I would like to show that this must be real. Assume that norm of F is 1 actually. Okay. Even if it is not 1, you can turn it into 1. Okay. So the lambda, the trick is this, the lambda can be written as norm of F square. Can I write it like that? So because this is 1 and this is same as. And if this is the case, then I can write this as lambda times ff, which is same as lambda f and f, which is same as af and f. Now I know that this guy is real, and hence lambda is real. Okay? If A is self-adjoint, then I know that this guy is real, and hence lambda is real. So that is part A. What will be part B? Simple things. What you need to show is that take two eigenvalues and corresponding eigenvectors and show that those two eigenvectors are orthogonal to each other. So let's take lambda and mu be two eigenvalues, and f and g are eigenvectors. Okay. Next. So obviously these are going to be in R because we showed in the first part that they are real. Okay. Such that what is true? So AF is lambda f and AG is mu g. Okay. So f and g are the corresponding eigenvectors to the lambda and f. So what I would like to show that f and g are orthogonal to each other. This is what that I would like to. Okay. I'm saying that let's begin with this calculation that lambda minus mu times fg. Okay. I can assume in addition that lambda is different from mu. Okay. Lambda is different from mu. I will show that this product is 0. If this product is 0 and this is non-zero, then this must be 0. Okay. So this is what my intention is. So if this is the case, then I can say that this is same as lambda f g and minus what? F mu g. Agree? So just multiplied this with the lambda and substituted lambda here. Multiply this with the mu and substitute mu in the second component because it is real. The conjugate of mu is going to be mu itself actually. Okay. And the trick is what? So this is same as AF G and minus this will be F AG. Okay? But A is self-adjoint, so I can put it here. This here. So I'm gonna get. I'm gonna get AF G minus AFN G, which gives me 0. Which gives me 0. Alright? And hence, since lambda is different from mu, so I have no choice except saying that f and g are 0. So f and g must be orthogonal to each other.
So f and g real number?
Huh?
Eigenvector.
They are eigenvectors. So if the lambda